Hello everyone, welcome to our video lecture series on HYSYS and UNISIM simulations, and today we are going to discuss a case study using HYSYS and UNISIM. This will be again mainly on a conversion reactor. These video lecture series have been organized by www.Unitoperation.com, and my name is Shekhar Bhattacharjee. Let us go directly into the problem statement here. As you can see, the sulfur dioxide is oxidized to, so this is a very standard reaction. Sulfur dioxide is oxidized to sulfur trioxide here in a small pilot scale reactor. So let's show the little bit of flow diagram here. Okay, sulfur dioxide and air are fed to the reactor maintained at 450 degrees Celsius and 1 atmosphere pressure. In fact, so this is the feed conditions are 450 degrees Celsius and 1 atmosphere pressure. Okay, the feed stream flow rates are as follows. So these feed stream flow rates are already given here. The reaction proceeds to 65% conversion. So this is my 65% conversion in the reactor. So this is a single pass reactor, and the products emerge from the reactor at 550 degrees Celsius. So this emerge at 550 degrees Celsius here. Okay, the reactor is surrounded by a water jacket. So there is a water jacket here, and the cooling water comes in, and of course hot water goes out. So this cooling water comes out at 25 degrees Celsius and goes out at 40 degrees Celsius. So the flow rate of water is adjusted accordingly so that this reaction temperature is maintained, so that the product comes out at 550 degrees Celsius. Okay, and you know that this is a highly exothermic reaction. The reactor is surrounded by a water jacket into which water flows at 25 degrees Celsius and exits at 40 degrees Celsius, and we have to use the Robinson equation of state. We have to calculate the heat of reaction from the simulation, and we have to calculate the product composition and the molar flow rate for each component. So let's go directly into the simulation environment here. We open a new case and go for the fluid package and add Robinson equation of state. And then we go for the view components, and for the view components we have to add the component. The first component to be added is sulfur dioxide, and then we have to add oxygen, then we have to add sulfur trioxide. Okay, and then of course there is already nitrogen present in the reactor, so we put nitrogen here. And again, water, although it's not either a reactant or a product, but it is a cooling water, but it has to be added in the components, although it is not a reactant or a product. So we just add water here. Okay, so all the components have been added, and as I mentioned that these are my sulfur dioxide, oxygen, nitrogen, the sulfur dioxide, these are my reactants, and this is my product. This is just an inert present in the feed stream, and this is just a coolant water. So once this have been added, we have to define, as usual, so we cross it out, the reaction, and definition for the reaction, this global reaction set comes in as a default. So it's the add reaction, and go for the conversion, and defining this one is very easy. Sulfur dioxide and oxygen, these are the reactants, and sulfur trioxide is the product. And we know that for the stoichiometry coefficient for this one is -1, this is -0.5, and this will be +1. So we go here, so we put here -1, and we put here -0.5, and this of course is going to be +1. Okay, once we have done that, and as you can see the balanced error is 0, that means this reaction is stoichiometrically balanced and automatically gives you the reaction heat, which of course you can calculate it from the standard heat of formation. You all know about that. We can go for the basis, and here based on the sulfur dioxide, and overall, although this should be a mainly gaseous phase reaction, you put 65% conversion because that's what has been defined here. The reaction proceeds to a 65% sulfur dioxide conversion. So if that is so, this has been totally defined here. So we just cross it out, and the important thing is that you have to do this reaction, highlight this one, and you have to add fluid package. This is very important. So once you have done that, you enter the simulation environment here, and then of course you choose the reactor. We have shown all these processes in our earlier videos. So we've been here, so we go bring the conversion reactor here. In the conversion reactor, as you can see, this 1 is my feed stream and 2 is my product stream. So I put here as 1 and 2 is my basically product stream, which is in the vapor gaseous stage. Although there will not be liquid, you have to put liquid here. You have to put it here just because of simulation, but of course the flow rate would be 0 here. And energy optional, here you put Q underscore reactor. That means the amount of heat that has to be taken out from the reactor. Okay, and then of course you have to add the reaction package, which you have already defined, global reaction. So this has been added. So that's the way we have defined the reactor is. As you can see, this is not red anymore, so this has been defined. Next, you just bring a cooler here, and in the cooler, as you can see, 3 is a stream coming in and 4 is going out. This would be at 25 degrees Celsius and this would be at 40 degrees Celsius. So what you do here, you just define this one as stream coming would be 3 and this would be 4. And here for the energy stream, you can see that this Q reactor, because that's what will be cooling, it will be taking all the heat loads of the reactor. So that's what the coolant is for. So you put the Q reactor. So, and of course the parameter, of course you have to put the pressure drop equal to 0. So once you have done that, so this has been defined. As you can see, this cooling water, which would be coming at 25 degrees and going at 40 degrees Celsius, would be taking the entire heat load of the reactor. So whatever the heat would be generated due to this exothermic reaction, so that would be the heat load on this particular cooler here. So now you have set it up. So only thing that remains now is to define the feed stream. So we go here, and first of course you define the composition. So you go here for the composition, and first one is of course the flow rate is 1922. 1922 is the but here this is not mole fraction, you go for the molar flow rate. So basically what we put here 1922, and this would be actually the mole per minute. That's what it says. Okay, mole per gram, mole per minute. As you can see here, if you come here, you see the flow rate is 192 mole per minute. Same with the oxygen, and the nitrogen is 7227. So we come here and do the same thing here, 1922. This is mole per minute. Here sulfur trioxide is not present in my feed, so that would be 0. Okay, and nitrogen would be 7227. So let's put this value as 7227. Again, this would be mole per minute. So we go here. So that's my nitrogen flow rate, and of course there will not be any water either as a reactant or product, so this will be 0. So that's the way we have defined. So that's a total molar flow rate. So we put that here, and automatically it comes in the form of mole fractions here. As you can see, we have sulfur dioxide, oxygen. There is no sulfur trioxide, but nitrogen is there, and there is no water. Okay, then of course for stream 3, which is for the water, so this is pure water. Let's call it, cannot be a pure water, but let's say this is water coming in. So this mole fraction would be 1. So for stream 3, we put here water as 1, the mole fraction coming in and going out. So it's the same for 4. So it's a water coming in and going out. So only thing now it stays is now we have to define the feed conditions here. Feed conditions, if you see, are the streams enter the reactor 450 degrees Celsius and 1 atmosphere pressure. So we go here and put here 450 degrees Celsius, 450 degrees Celsius and 1 atmosphere pressure here. So this is an atmospheric pressure reactor. So we go here and put 1 atmosphere pressure reactor. So automatically the entire feed stream is defined. So only thing now what we have to do is here you can see the product stream is coming out at 550 degrees Celsius. That's given in the my problem statement. The products emerge from the reactor at 550 degrees Celsius. So we go here, and for stream 2 this temperature would be 550 degrees Celsius. The moment you do that, you see, so that automatically is defined. Okay, now here you see for cooling water load, what you need to do is that you see the water is coming at 25 degrees Celsius, going at 40 degrees Celsius, but the heat load is taking the entire heat load of the reactor, which has already been defined now. So we go for stream 3, the temperature will be 25 degrees Celsius, and of course it is at the coolant water is at 1 atmosphere pressure. So you put here and 1 atmosphere pressure, and again, so you don't have to put the flow rate, because it will automatically calculate the flow rate that would be required to keep this temperature. So keep this temperature coming out at 550 degrees Celsius. So here the outgoing temperature would be 40 degrees Celsius. So the moment you do that, and of course automatically you see all the streams have turned blue. Okay, and if you want to see the water with the heat load, so that is the amount of heat that has to be taken out from the reactor. So that's the amount of heat that has to be taken out from the reactor. And what is the flow rate of the stream coming in? So here, as you can see, the kilomole per hour mass flow is 7.46 10 to the power 4. That's kilogram per hour of heat for the coolant water stream flow rate that is required to keep the maintain the product temperature at 550 degrees Celsius. If you want to see this kilogram per minute, what you really need to do is go to the tools, and you go to the preferences, and you go to the variables, and then let's say you put a new user here, and you go all the way down to mass flow rate. So here is the mass flow. You put here, so let's say kilogram per minute. Once you do that, automatically you can see this comes as kilogram per minute. So 1274 kilogram per minute of water, coolant water flow rate is required to maintain this temperature at 550 degrees Celsius. Okay, and of course you can get the compositions of your product stream and everything else. So that's a way you simulate a conversion reactor which is jacketed, and the heating load and the cooling load of the conversion reactor. I'll see you next time with another video.